If we're drawing bell curves and studying proportions, we're using Z, aren't we? Just like we did back with confidence intervals. You're studying proportions, you're drawing bell curves, you're using a Z distribution. Yes. So I put 4 there. As we go through these next 4 weeks together, we'll pick up each of these guys. We've already seen C and T. Chi-square and F come later. We might not even get to F. We'll see how time goes. Definitely get to chi-square. That might be the last thing we do. But the idea is, depending on what you're studying, you're going to want to look at the correct distribution. So since we're talking about a proportion, a binomial represented by the normal, boom, that's a Z. Okay, doke? Fair enough so far? I wasn't going to have you turn these first few in, but you will be turning them in eventually. That's actually not a bad idea. We can just make in-class quizzes on the fly as we need them. Yeah, that's not a bad idea at all. We totally can. Would you guys be down with that? Like, we'll do a few for practice. That's not a bad idea. I hadn't thought about that, but if we got a template in front of you, we can decide which ones we want to hit. That's not bad, Stacy. Thank you. That's good. That's real good. That's good. Okay, so here we go. Test statistic. Now, the test statistic is very much like a critical value from a confidence interval. In other words, remember on that curve over there, I had that 10.1%, and I said, where is it, where is it, where is it? I don't exactly know where it is. This is going to tell us where it is. It's going to tell us at what point of the curve it lies. So what I need to do is I want to redraw that curve. I'm going to put it up here very small in the corner. Yes. If we're using the Z distribution, I've got to put a 0 in the middle. Because that's what's in the middle of the Z distribution, is 0, yes? Okay, he's going to be in the middle. Somewhere, courtesy of Tim, somewhere over here is a 5% area range. It's cut off by a Z-score, and it goes out 5%. I think, and you guys can check me what's the normal on this one, I think that's negative 1.645. Is that, you got it, Michael? This guy right here, negative 1.645. You don't have to memorize that in your mind. You don't have to know that. But some people want to know, okay, how far over do I have to get until I'm past that point? You don't have to know it because soon technology is going to take care of stenonormal. Did you use stenonormal to do it, Michael? Yeah. Excellent, thank you, sir.
It didn't give me the 5 at the end.
Oh, I thought it was 1.65. 1.64, totally fine. We'll call it that, that's fine. I'm probably putting 2 things together and getting it wrong in my head anyway. It's about negative 1.64 standard deviations down. Some people are going to go, wait a minute, time out, I thought it was 2. Isn't 2 standard deviations 95%? That was a 2.5 on each side, was negative 2 and 2, right? This is one-sided confidence. We've got to take that 2.5 that's over here, bring it over here, which shoves this one up a smidge. Does that make sense? If you're doing 2-sided intervals, which I'm not saying are not useful, we'll come back to those. You like them sometimes. But if you're doing a 1-sided one, that's going to be your cutoff value. So our job now is to turn our data that we have from our experiments into a number, a test statistic, that will fall on that horizontal line somewhere. And we're going to use a Z-score, just like we did in 243. If you remember what a Z-score looks like, this is the general Z-score. Does anybody remember what the general form of a Z-score is? Z equals, it's 3 things. Remember what the 3 things are? Oh, you're a little bit ahead, Stace. Go back even further than that. Pre that. That was an adjustment for sampling. But a general Z-score, we do have to use that, but not just hold that thought for now. What was in it? Give me one of the variables that's in a Z-score calculation.
X minus 1 over standard deviation.
That was exactly what it is. It's your raw data, which we called X back in the day, minus whatever the average of the distribution was, all over the standard deviation little sigma. It's perfect. That is the cornerstone of the rest of this course. It's all about that, but we have to make adjustments for it for each of the types of data. And that's what you were getting to, Stacy. Thank you. So, basically, any test statistic is going to be like this. It's going to be some kind of data you collected minus some kind of hypothesized average, all divided by the hypothesized standard deviation. All we've got to do is make the adjustment for the data set, the sampling adjustment that we had to make with the central limit theorem. So that's the general Z-score. So our test statistic adjustment And we're going to do one of these for each of the tests that we do. This is why I don't want to turn this particular one in as a quiz. I want this to be the template we work off of. And once we get a couple under our belt, we'll start heading with it, for sure. It's still going to be Z. It still has to be Z. We're still going to be Z. Mike, what are you thinking of right now? Keep what's on your mind.
Well, shouldn't that mu be P then? Because...
That's the adjustment, brother. Thank you, thank you, thank you. Michael has made the connections. I went in a timeout. This is mu and sigma. First of all, they're population parameters. Secondly, these are proportions. This is the general form of any test statistic. It's sample data minus population data over variability. We have to adjust each of those for each of the particular contexts that we're in. So, thank you, Michael, for bridging the gap. Our sample data in this, remember what it was? Stacy actually gave it to us about half an hour ago. The 10.1, which was p hat. That's what's going to go here. Is this blue visible? Can you guys see what's with the blue marker? It's starting to die a little bit. Good. Minus the population data. Stay nice and brave. Little p. That's the assumed population data. It was the 12%, which we call little p. Now you might remember we actually quoted the numerical value of this one. I want to put this here, and put this over here. I want to do the numerators first. This was 10.1%, 0.101, yes? 0.101.
Do you always,
Say that again.
do you always put it to the decimal point?
Say that again, JC,
Do
I'm
you
sorry.
always put it into the decimal point? I can't.
Me personally, I do because I can't stand the other way. Because in order to do any math with it, you have to kind of change it. Is that fair?
Yeah.
Yeah, it just makes it easier. You could do it in percent form, but the computers won't like it.
Yeah.
Population proportion, 12%. And we actually ran this earlier, didn't we? Negative 0.019. Does that sound familiar? It was a discussion Tim and I had about 20 minutes ago. Negative 0.019. Do you remember that? What was that discussion about? 1.9% lower, right? And that's when Tim said, well, in my opinion, that's not low enough. And I said, I'm not going to get into fist fight with you, brother, because you kicked my ass, number one. But number two, we can't decide if 1.9 is significant until we do what? And somebody else asked for something else that we're just about to create. On the interval, we got to make the margin around it. Yeah, we got to figure out how many standard deviations the 1.9 down is. If the standard deviation is 5%, that's nothing. If the standard error, let me use the correct term. If the standard error or the margin of error is 5%, then 1.9% doesn't even get out of that margin. But if the margin of error is very, very, very tight, then it does. So the question is, what is the margin? And that's what this measures. It's so important. This is such an important part of the computation. But of course, the media always ignores it. Divorce rate plummets in the recession from 7.6% to 7.5%. Maybe, but only if that 0.1% is outside of two margins or two standard errors, right? So that's the whole point, is it significant? Well, here's where this comes in. In order to actually calculate this bad boy, it's a square root. Stacey, you were quoting this earlier, thank you. It's a square root. Now here's the goofy part. You might remember this, you might not. It's okay if you do or don't. It's P times Q over N. That might look vaguely familiar from the confidence interval. So I made you do the penny one by hand a couple weeks ago. And this was essentially the calculation that we did. The difference from a couple weeks ago was we had P hat and Q hat, if you remember. That's because we had sample data. We are testing our sample data against the population. So since we're slapping this bad boy on the null curve, we have to use the null P and Q. Does that make sense? Because we're comparing it to the 12% curve. This 0 here is really indicative of the 12%. So we have to play by his date, his 12% and his 88%. Lauren, ask me that question.
We had a critical score before a radical when we had
Right, it's this guy?
no,
Oh,
I mean,
good. But we can't use that because this is a one-sided versus a two-sided interval. That was going to be a little too far down. Is that fair? That would be a 97.5% or a 2.5% alpha level. We'll come back to him too. Don't worry about that. We'll come back. That's if you really don't want a false positive. If you really don't like false positives, you got to increase your confidence. And we'll talk about why momentarily. Good. Exactly. Here we go. Yes. 12%. 88%. Over 1,000. That's the adjustment for the sampling size. You have to divide that bad boy by 1,000. He has to be in. Because as you sample more, the curve tightens. I'm always going to draw the curve the same lame way. it might not be indicative of how tight the curve actually should be. So just realize that. I apologize, my art skills are not the greatest. What does that end up being? Make sure I can do this right. I always screw these up. I'm going to do it. You guys tell me if I'm right or not.
Can't see it, so.
That's okay. I'm going to tell you. So the top is about 11%-ish. It's not really percentage points, it's squared. I get 0.0103 for this number. Check me on that, if you'd be so kind. 0.0103 rounded to 4 decimals. We got that? We got it good? Thank you. We got agreements?
Wait, what?
I got 0.0103 for this number here.
Yeah.
Was that good? Good. So we're going to divide that by 0.010. Well, hot damn, that's tiny little margin. Remember, that's 2 standard errors. That's the equivalent of going out 2 standard deviations. This went out further. This went out 1.9. This only goes out 1.03. The question is, I suck at division. So now what I'm going to do is I'm going to divide that by that and see what the number comes out to be. Yeah? Because now I know how big the change was. This is the margin. This is the margin on the interval. Let's divide negative 0.019 divided by that. I end up with negative 1.85 to 2 decimals. Let's make sure we all get that. I get z equals negative 1.85 to 2 decimals. Let's make sure that everybody's getting the same thing I'm getting. Make sure I'm doing the math right. Trusting that this is the first and last time you'll ever have to crunch one of these out in this way. Because the machines will do it for us soon. But I need you guys to see what the hell's going on. You need to know especially what that guy is. He's huge. You can see if your sample size goes down, he goes up. So significance might only exist because of a large sample. Ooh, that could be a problem. We'll come back to that. We'll come back to that. Everybody getting this?
1.84.
Oh, 1.84? Good. I'm not going to get just about that. So the question is, and it's negative, right? Don't forget that.
Yeah.
We know it has to be negative because we had a negative number here divided by a pi. So the question now is, where did it land? Where did that land? That is a z-score. Which, good, JC, you're looking in the right place, sister.
A little bit.
Uh-huh.
A little bit outside of that 5%.
Oh, yeah. So the cutoff here was negative 1.64, yes? Where did we land? We landed right here. I'm going to put z test stat, if that's okay with you guys. For the test statistic. It is negative, isn't it? Right. It's negative. You see that, right?
Yeah, I just missed the negative part.
Oh, God! Well, if you miss the negative part, what's your flu vaccine doing?
Killing me.
It's making people sicker. Because it's equally significant on the other side of the curve. Yes, that's a good point. Thank you, Stacy. I know it's comical. I'm glad you brought it
I
now.
was like, why are you going that way?
Because that's what the data shows. If it's positive, you actually go the other way. Yes, thank you. Good catch. Negative 1.84 or 5 or 4, whatever you guys are saying it is. But it fell to the left. I heard somebody say it fell a little bit to the left. Thank you for that. It did. It only fell a little bit to the left.
It's not the 0.0000001.
It's not good. So, Kate, thank you for the segue. What is the p-value on that? Because the next question is, what is the p-value? Now, to answer that question, you have a couple options. It depends on how you learned in 243. With us, we learned it was the normal. With Donna, you guys most likely use charts, I'm guessing?
No.
You didn't use charts. Use the calculator as well? Okay, beautiful. So however you learned it, this thing carries a p-value. So what you have to do is, starting at that negative 1.85, you have to figure out how much area is to the left of that negative 1.85. So if you use the normal, this is probably the last time you'll use the normal, I'm guessing, in this class, because the TIs have a built-in likes the normal, it's actually better. So what are you going to put in? Forwards or backwards problem?
Forward.
Most definitely forwards, because you have the z-score. Shading to the left, I'll do it with you. I feel left out now. Okay, we're using stonormal. And if you guys don't have stonormal, please don't worry. Because I said this is the first and last time I'll probably use it in 244. It worked great in 243, but we've got better tools soon. So program stonormal, there you are. It's a forwards problem, shades left, at negative 1.84, whatever you guys said it was. Here it comes, there's the curve. That is your p-value right there. 3.29% or 3.3% or less than 5%, however you want to say. That's your p-value. That's your p-value. Go, Stace.
Can we go back to this, with the test statistic, which is correct about variable? Is that just what we wrote out right there?
Correct variable, test statistic.
Okay, got it.
Yes, ma'am. That's why I call him z-test stat over here. And I like the image too. I didn't know how to put the image on your paper. Are you guys able to squeeze the curve onto the template page? Right, if you're drawing these, is there room for the curve? I didn't know how to set it up so there was. Maybe I'll redraw them so there is. On the back? So maybe I shouldn't make them two-sided, or make them shrunk down so you can fit the curve. Let me redesign it. I'll use a smaller font maybe and shove things over so you can put the curve in.
But leave enough room for Greg.
Of course. Of course. Well, if I make the font smaller, that should fix that. I'll deal with it. This is like a beta release, so I'm trying to make it as useful as possible. If I see you flip-flopping back and forth, that's hopefully, I don't want it to get too detrimental.
You could move half of it to the back.
I could, but I'd like to have it all on the front, so you don't have to go back and forth. I'll come to that. I'll figure that
But
out.
I mean, like, make it bigger so that it goes.
But then I want to make sure we have room for this too.
That's what I meant.
Okay, we'll come back.
I'm having-
Email me ideas. Email me ideas.
Sean, I'm having a brain fart with this normal thing.
Yes.
When you I typed in negative 1 point.
You-
You
1.8, forward, left, negative 1.85,
And
enter.
excuse me.
It might be a corrupted code. We'll take a look. Or don't worry because you have a built-in in a moment that'll
I
take
know,
care of
so
it.
I was like, I don't know.
Or don't worry about that. We'll show you the built-in. It actually takes care of all this for you. But the problem is the built-in that I'm going to show you does all of this automatically, which is great. Except for the fact that then it's a black box. If you put data into it, an answer comes out of it, you don't know where it came from. I wanted you to see it once to make sure you knew that it was actually stemming from this. JC, was that you? Go
Yeah,
ahead.
is it always moving forward?
Is it always going to be
Forward.
to find a p-value? Yes, because you're going to have a z-score on the axis. But don't worry about that because honestly, this might be the last time you use that. Maybe. I'm thinking it might be based on the built-in that you haven't seen yet.
But, so the built-in is always forward, it'll do it.
And it never asks you for 4, it just does
Okay.
4 automatically. So hold that thought. Hold that thought. Give me 5 minutes maybe. Other questions right now? So we've got a test statistic, but we've got a p-value, yes? So now it says circle the correct phrase and complete the conclusion based on your p-value. So what was the whole point of setting up this little region over here that was 5%? Say that again, Michael. Right. This is, if you will, the vaccine is working. This is, if you will, the vaccine is not working. Does that make sense? So, I said it appears or does not appear that, dot, dot, dot. It appears, so Stacy says circle appears. What does it appear? It appears that the vaccine, good, is working. You can phrase this a number of different ways. One way is to say it appears the vaccine is working. I got no problem with that. You could also, if you want to be more specific, it appears the vaccine is lowering the flu rate below 12%.
By a significant amount.
By a significant amount. Good, good. Realizing that that opens up a can of worms that you're gonna have to support later, maybe. Because what's the next question somebody might ask? How much did it lower it? And you gotta admit, well, your sample data came back at 1.9%. But I can put a confidence interval on that and give a plus or minus. So realize, I like all those answers. It appears the vaccine is working. It appears that it lowers it a significant amount. Good, very good. Angie, ask me that question. Oh, you good, just track. Good, perfect. Last question. Which type of error could we make? Have made right now. Remember, we listed 2 errors before, but we can only make 1 based on our p-value. I have vote for type 1. Second for type 1. All in favor of type 1? All opposed? We need discussion on this? Of course we do. Why is it a type 1 error? Potentially.
Because from our data, it showed that it was working. And
Our vote is that it's working. If we say it's working, either
it is or it isn't.
it is or it isn't. And if we say it is, and in fact isn't, that means it's a false positive, which makes it a type 1. Thank you. That's perfect. How's that? So you're done. You're done. You did your test. Step 9, if you will. Step 9 is the conclusion that you would read about in a journal. Or you would read about on a little piece of paper that goes with the medicine. You know that little piece of paper you never read with your medicines? It would say it in there, how the results of the test. Step 10 is the nod you should do every time. We could be wrong. It could be that we didn't get significance. As a matter of fact, whatever that was, what was the p-value? 3.2%? Probably 3.3% probably isn't small enough for FDA drug trials. They're going to want it super low, like super, super low. Because right now, what you just decided, with your conclusion, is that here is the curve of those not using the vaccine. You have just concluded that there most likely is another curve lower than that one of those with the vaccine. They're separate curves. That's your conclusion. Just like green tea and breast cancer. There's two curves. There's the curve of those who don't use the vaccine, and there's the curve of those who do use the vaccine.
You should send this to all the lovely statistic people who are writing their journals out there so that they can write in English.
The sad part is they've all taken this class, but the problem with the way academia treats this class is, if you look at where I am compared to where any other instructor is in the state of Oregon right now in 224, I'm 3 weeks behind everybody. I'm always 3 weeks behind, because I'll spend an hour on a problem like this to make sure that you know exactly what the number that's coming out means. That's what I care about. I can rush you through, I could have you guys do p-values in week 2, but all you're doing is regurgitating what a p-value is, and at some point it's so subtle that it's lost. It's lost. You start quoting it wrong. Oh, it's a chance a null hypothesis is right. I hear that all the time. P-value, it's a chance a null hypothesis is right. How dare you? You have no idea if the null hypothesis is right or not, and you don't. You sure as hell don't know how to measure it. It's either right or it's wrong. What you're looking at is you're looking at the association of a null belief with your data. How well do they sync up? This one only syncs up at 3.3% or whatever it was, 3.2%. That's hardly any sync up at all. That means there's a contradiction. That means assuming the vaccine's not working and getting data that shows it is a contradiction, which means it looks like the vaccine actually is working. Is that fair? Yeah, and I agree with you, Kate. Everybody should kind of learn it this way, in my opinion. Because I think students leave here with a really, really rich understanding of what a p-value is. Because honestly, if you walk out of this class knowing what a z-test is, what a t-test is, what a p-value is, I am a stoked dude. I'm a stoked dude. Everything else is gravy. Now, before I kick you out of here, let's learn the shortcut. Because this template, I want you to complete this template every time, of course. But what I want to make sure also that you have is steps 7 and 8 can get a little bit obnoxious. They can get a little bit obnoxious, 7 and 8, especially as these get more and more complex. These test statistics can get fairly complex. When we start doing, when you look at the bike break data that me and Max collected, it's going to get fairly large and fairly huge and fairly obnoxious. So it's nicer to let technology deal with that, and we focus on the interpretations, which is kind of the important part anyway. So let's go to our TIs real quick. Okay, good. Let's stop.